Counting the planets in our solar system is something every child learns in school. 8. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. 8 planets. Clean. Settled. Done. Except, what if that number is wrong? Not because we miscounted, not because Pluto deserves a second chance, but because somewhere beyond Neptune, in the frozen dark at the edge of the solar system, something is out there. Something massive. Something whose gravity is silently bending the orbits of distant worlds in patterns that no 8-planet model can explain. Astronomers call it Planet 9, and the math describing it is not speculative. It is precise. Specific orbital predictions, a specific mass range, a specific region of sky where it should be hiding. But here is the part that nobody tells you. If Planet 9 is real, if it exists, there is a serious and growing body of scientific evidence suggesting it did not form here. It did not condense from the same disk of gas and dust that made Earth, Jupiter, and everything else we call home. It came from somewhere else, another star system, another sun, cast out into the void billions of years ago, drifting through interstellar darkness until our sun's gravity reached out across the void and pulled it in. A rogue world, captured, imprisoned, hiding in the outermost dark of our own solar system. And the evidence suggesting this happened is far stronger than anyone expected. To understand how a rogue planet could be captured by our sun, we first need to understand what rogue planets actually are, and how many of them are out there. A rogue planet, also called a free-floating planet or interstellar planet, is exactly what the name suggests. A planetary mass object that does not orbit any star. It drifts through the galaxy in gravitational isolation, bound to nothing, illuminated by nothing, travelling through the interstellar void at whatever velocity it was given when it was ejected from its original planetary system. These objects are not rare. They are not exotic. They are, by current estimates, extraordinarily common. In 2021, the microlensing survey conducted by the MOA collaboration, Microlensing Observations in Astrophysics, a joint Japan-New Zealand project operating from the Mount John University Observatory in New Zealand, published statistical results suggesting that rogue planets in the Milky Way outnumber stars. The survey detected microlensing events, brief, precise brightenings of background stars caused by the gravitational lensing effect of a massive object passing between the star and the observer, at rates consistent with a population of Earth mass to Jupiter mass free-floating objects that could number in the hundreds of billions. Possibly more than 1 trillion when smaller objects are included. Let that settle for a moment. More rogue planets than stars. The galaxy is not a collection of stellar systems with occasional strays between them. It is a sea of drifting worlds, each one the remnant of a planetary system formation process that cast it out. And the stellar systems are the islands in that sea. Where do these objects come from? Planet formation is a violent, chaotic process. From the rotating disk of gas and dust surrounding a newly formed star, the protoplanetary disk, dozens or hundreds of planetesimals, protoplanets, and eventually full planets form and interact gravitationally with each other and with the disk itself over millions of years. In many planetary systems, particularly those that form multiple gas giants, the gravitational dynamics of these interactions are highly unstable. Planets scatter each other. Close encounters transfer energy between bodies, sending some inward, where they may collide with other planets or be consumed by the host star, and others outward, where they may be ejected entirely from the system if they receive enough kinetic energy to exceed the escape velocity. Simulations of planetary system formation consistently show that ejection is not an unusual outcome. It is a common one. Models of the formation of our own solar system, including the influential NICE model, developed by a team of researchers including Alessandro Morbidelli at the Côte d'Azur Observatory and published in Nature in 2005, suggest that the early solar system may have contained 5 gas giants rather than 4, with the 5th ejected through a gravitational interaction with Jupiter approximately 700 million years after the solar system formed. Under this model, our solar system itself produced a rogue planet. So rogue planets are abundant. They are the natural byproduct of planetary system formation across the galaxy. Hundreds of billions of them drift through the Milky Way, passing through the gaps between stellar systems over timescales of millions to billions of years. and this raises an obvious question. If rogue planets are that common, and stars are moving through a galaxy populated with them, what happens when a star comes close enough to a rogue planet for its gravity to matter? Capture. Under the right conditions, a star can gravitationally capture a free-floating planet, decelerating it below the local escape velocity and binding it into a permanent orbit. The rogue world becomes a new planet of that stellar system, inserted not from the inside out through formation, but from the outside in through capture. This process is theoretically straightforward. In practice, it has a significant constraint. A simple two-body gravitational encounter between a star and a rogue planet cannot result in capture. The laws of conservation of energy and momentum are exact. A planet approaching a single star on a hyperbolic trajectory, moving faster than escape velocity, will swing around the star and continue on its way. For capture to occur, energy must be transferred away from the approaching planet. A third body must be present to absorb that energy. Another planet, another star, or the gravitational dynamics of a close multi-body encounter. In the dense stellar environment of the Sun's birth cluster, such three-body encounters were not rare. They were common. Our Sun did not form alone. No star does. Stars form in clusters, dense, young, stellar associations where hundreds to thousands of stars occupy a relatively small volume of space over the first tens of millions of years of their lives, before the cluster gradually disperses as the stars drift apart under galactic dynamics. The Sun's birth cluster is estimated to have contained somewhere between 1,000 and 10,000 stars, packed into a region a few light-years across. In this crowded environment, close stellar encounters occurred regularly. Planetary systems overlapped. Gravitational interactions between the forming systems were continuous and complex. In this early chaotic period, the conditions for planetary capture were far more favourable than they are in the current solar system, which has been drifting through relatively empty interstellar space for most of its 4.6 billion-year history. A rogue planet approaching the early Sun could have had its trajectory altered by a simultaneous interaction with another nearby star, or by Jupiter's massive gravitational field, in a way that reduced its velocity below the Sun's escape velocity, inserting it into a distant elongated orbit. And that distant elongated orbit, precisely the kind of orbit that a captured world would settle into, is exactly the signature that modern astronomers are finding in the outer solar system. But that is not the full story, because the evidence for something massive and anomalous hiding in the outer solar system does not begin with theory. It begins with observations, specific, precise, reproducible observations of small bodies in the outer solar system, whose orbits cannot be explained by the 8 known planets, and which point, with remarkable consistency, toward the existence of something massive and hidden in the dark beyond Neptune. The story of Planet 9 begins with a pattern nobody was looking for. Sedna was discovered on November 14, 2003, by a team led by Michael Brown, Chad Trujillo, and David Rabinowitz using the Samuel Oschin telescope at Palomar Observatory in California. At the time of its discovery, Sedna was approximately 90 astronomical units from the Sun, 1 astronomical unit being the average Earth-Sun distance, roughly 150 million kilometers. Sedna's highly elongated orbit carries it out to approximately 937 astronomical units at its farthest point, farther than any known solar system object at the time, farther even than the inner edge of the hypothetical Oort cloud. What struck the Discovery team immediately was not Sedna's distance, but its orbital characteristics. Sedna's perihelion, its closest approach to the Sun, is approximately 76 astronomical units. This places it well beyond Neptune's gravitational influence, and yet it is far too close to be an Oort cloud object, whose perihelia are typically thousands of astronomical units from the Sun. Sedna occupies an orbital region between roughly 50 and 1,000 astronomical units that existing models of solar system formation had not predicted would contain objects on such extreme detached orbits. Something had to have put Sedna there. Something external, a passing star in the Sun's birth cluster perhaps, or a distant massive body, had perturbed its orbit into this bizarre configuration. For nearly a decade, Sedna remained unique. A curiosity, an anomaly requiring explanation but insufficient to demand any specific one. Then, in 2012, Chad Trujillo, now at Gemini Observatory, and Scott Shepard at the Carnegie Institution for Science discovered a second Sedna-like object, 2012 VP113, nicknamed Biden by the Discovery team. With a perihelion of approximately 80 astronomical units and an orbit equally detached from Neptune's influence, it joined Sedna in a growing category, inner Oort cloud objects, or extreme trans-Neptunian objects, whose orbits could not be explained by known planetary gravitational dynamics. And then the pattern emerged. Trujillo and Shepard noticed something in their data. The argument of perihelion, a parameter describing the orientation of an elliptical orbit in three-dimensional space, was clustering among the known extreme trans-Neptunian objects. Not randomly distributed, as would be expected if these objects' orbits were shaped by random processes, clustered, aligned, as if something was shepherding them, corralling their orbital orientations into a preferred configuration through repeated gravitational nudges. This was not an artifact of observational bias. Surveys are not more sensitive in some orbital orientations than others, in ways that could produce this clustering. It was a real signal. Michael Brown at the California Institute of Technology, the same Brown who had led the Sedna Discovery team and who had been instrumental in the reclassification of Pluto to dwarf planet status in 2006, saw the Trujillo-Shepard paper and immediately recognized the orbital clustering for what it implied. He brought in Konstantin Batygin, a planetary scientist also at Caltech, to run the gravitational dynamics. Brown and Batygin's analysis, published in the Astronomical Journal in January 2016, concluded that the orbital clustering of 6 extreme trans-Neptunian objects was statistically consistent with gravitational shepherding by a single distant massive planet. The probability of the clustering occurring by chance, less than 0.007%, not conclusive by itself. Small samples can produce spurious correlations. But the direction of the implication was clear. Something massive, something distant, something undetected by any existing survey. Planet 9, as Brown and Batygin named it. A hypothetical world with a mass approximately 5 to 10 times that of Earth, a super-Earth or sub-Neptune, orbiting the Sun at a distance of perhaps 400 to 800 astronomical units on an elongated orbit inclined to the planetary plane by roughly 15 to 25 degrees. Now here's where it gets truly strange. As additional extreme trans-Neptunian objects were discovered in subsequent surveys, the number of confirmed clustered objects growing from 6 to more than 20, and as Brown and Batygin refined their analysis, the predicted orbit of Planet 9 converged on a consistent set of parameters. But a consistent orbit immediately raises a question that points directly toward the capture hypothesis. Is this the orbit of a planet that formed in the solar system, or is it the orbit of a planet that came from somewhere else? Planets that form within a solar system do so within the protoplanetary disk, the flat, rotating structure of gas and dust from which all solar system bodies originate. Formation within the disk produces objects whose orbits are aligned reasonably close to the disk plane, the ecliptic plane in our solar system, which all 8 known planets orbit within a few degrees of. High orbital inclinations are not natural products of in-disk formation. They are the products of dynamical perturbation, gravitational interactions that tilt an orbit away from its original alignment. Planet 9's predicted orbit, though inclined by 15 to 25 degrees to the ecliptic, is not impossible for an in-situ formed object. Neptune's migration in the early solar system could, in principle, have scattered a super-Earth onto an inclined distant orbit. But the combination of its predicted distance, inclination, and eccentricity sits uncomfortably at the edge of what standard solar system formation models produce naturally. The orbit is, as planetary scientists say, dynamically warm. It has been heated, stirred, perturbed away from the neat low-inclination configuration expected for an in-situ body. It looks, in other words, exactly like what a captured rogue planet would look like. This is the assessment that Amir Siraj and Avi Loeb, a student mentor pair at Harvard, Siraj pursuing his undergraduate degree and Loeb directing the Institute for Theory and Computation, developed in a paper published in 2020. Their analysis modelled the capture probability for a rogue planet during the Sun's early residence in its birth cluster, computing the rate at which free-floating planets would have passed through the densely populated stellar environment close enough to the young Sun for 3-body capture interactions to occur. Their conclusion: During the approximately 100 million year period the Sun spent in its birth cluster, gravitational capture of a rogue planet was not merely possible, it was reasonably probable. Under plausible assumptions about the density of free-floating planets in the cluster environment and the frequency of close stellar encounters, the probability of capturing at least one rogue planet during this period is estimated at roughly 0.5 to 2% per star. 0.5% sounds small, but applied across hundreds of billions of stars in the galaxy, it implies that hundreds of millions of stellar systems harbour captured rogue planets in their outer reaches. Our solar system is not uniquely special if it has captured one. It is simply a member of a common but rarely identified class. This means something profound about the solar system boundary itself. What we call the solar system, the family of objects gravitationally bound to the Sun, may include a world that spent part of its history orbiting another star, or no star at all. A world born in the darkness between the stars, or exiled from its original home billions of years before Earth formed. And the question of what that world is like, its composition, its temperature, its history, is where the implications become genuinely staggering. A rogue planet that spent billions of years in interstellar space would be cold, profoundly cold. The surface of a Neptune-sized world drifting in interstellar space, receiving no stellar radiation, would cool to temperatures near absolute zero over hundreds of millions of years. But cold surface does not necessarily mean dead interior. Neptune-sized and super-Earth-sized worlds retain internal heat for billions of years. Radioactive decay within the rocky interior provides a continuous heat source that maintains elevated temperatures in the deep interior long after the surface is frozen. An internal heat combined with the possibility of a thick hydrogen and helium envelope creates the conditions for liquid water beneath a layer of ice, a subsurface ocean analogous to the ones now believed to exist on Europa, Enceladus, Ganymede, and Titan. If Planet 9 is a captured rogue world, cold on its surface, dark in the outer solar system, receiving perhaps 1/100,000th of the sunlight Earth receives, it could nonetheless maintain a subsurface liquid water environment driven by internal radiogenic heat. Not a warm, sunlit ocean, a cold, dark subsurface ocean, sealed beneath kilometers of ice, warmed from below by the radioactive decay of uranium, thorium and potassium in the rocky mantle. What lives in such an ocean, if anything lives there at all, is a question that, at the moment, has no answer. But it is a question that is no longer purely speculative. It follows directly from the physics of planetary heat retention and the growing evidence that subsurface oceans are common in the outer solar system, even on bodies far from the Sun. The implications of this discovery are almost too vast to comprehend. A captured world, orbiting our Sun on a vast elliptical path, harbouring, potentially, a liquid water environment that has been isolated from the rest of the universe for billions of years. A world that may hold answers to questions about life in the cosmos that we have not yet had the instruments to ask. The case for Planet 9's existence rests on several independent lines of evidence, each compelling individually and collectively forming an argument that is increasingly difficult to dismiss. The orbital clustering of extreme trans-Neptunian objects, the original signal identified by Trujillo, Shepard, Brown and Batygin, has grown stronger with additional objects. Critics of the Planet 9 hypothesis correctly noted early that the original 6-object clustering could be influenced by observational bias. Surveys search preferentially in certain regions of sky, and a clustered search could produce apparent orbital clustering without any real physical cause. But as the catalogue of extreme trans-Neptunian objects has grown, and as surveys designed specifically to test for observational bias have been analysed, the clustering signal has not disappeared. In 2021, Nathan Kaib at the University of Oklahoma and Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux published a reanalysis arguing that some fraction of the clustering could be explained by the gravitational influence of the galactic tide, the differential gravitational pull of the Milky Way's mass distribution on distant solar system objects, without requiring Planet 9. Their work reduced but did not eliminate the statistical case for Planet 9, and it was itself critiqued for underestimating the clustering signal in the highest quality, least biased subset of the data. The debate continues. That is what healthy science looks like. But the observational data has continued to accumulate in ways that are more consistent with Planet 9 than with any alternative. A second, independent line of evidence comes from the orbital inclinations of trans-Neptunian objects more broadly. Objects in the outer solar system show a distribution of orbital inclinations that is broader and more complex than standard solar system formation. Models predict without an additional distant perturber. Specifically, the existence of objects orbiting the Sun at extremely high inclinations, nearly perpendicular to the ecliptic or even in retrograde orbits, travelling in the opposite direction to the planets, is difficult to explain without a distant massive object pumping orbital inclinations through gravitational perturbation over billions of years. Batygin and Brown's 2019 paper in the Physics Reports journal, a comprehensive review of the Planet 9 evidence, specifically addressed the high inclination population. Their simulation showed that Planet 9's gravitational influence naturally produces the observed population of highly inclined trans-Neptunian objects through a mechanism called orbital secular resonance, a gravitational interaction operating on timescales of millions to billions of years that progressively drives orbital inclinations higher in a specific fraction of outer solar system objects. Reproducing this population without Planet 9 requires alternative mechanisms that are either physically implausible or inconsistent with other observational constraints. A third line of evidence is the anomalous tilt of the Sun itself. Our Sun's rotation axis is tilted by approximately 6 degrees relative to the plane of the planetary orbits, the ecliptic. This is a genuine anomaly. In standard solar system formation models, the Sun should be rotating with its axis nearly perpendicular to the ecliptic, since both the Sun and the planets formed from the same rotating protoplanetary disk. The 6-degree tilt requires explanation. Batygin and Brown proposed in 2016 that Planet 9's mass and orbital inclination, acting over the 4.6 billion-year history of the solar system, would have exerted a systematic gravitational torque on the entire planetary system, gradually tilting the orbital plane of the planets relative to the Sun's equator by precisely the amount observed. The calculation matched the observed 6-degree tilt with the same Planet 9 parameters predicted by the trans-Neptunian orbital clustering. This is not a coincidence, or rather, if it is a coincidence, it is a remarkably precise one. The same hypothetical object, with the same mass and orbital parameters, simultaneously explains 3 independent observational anomalies: the orbital clustering of extreme trans-Neptunian objects, the distribution of highly inclined outer solar system bodies, and the tilt of the Sun's rotation axis. Independent lines of evidence pointing to the same solution. Now, why does the capture hypothesis fit better than the in situ formation hypothesis for this object? To understand this, we need to engage with what planetary formation models actually predict for objects in Planet 9's predicted orbital location. Standard solar system formation models, including the NICE model and its successors, predict that the region beyond approximately 100 astronomical units from the Sun is essentially empty of planet-forming material. The protoplanetary disk that gave rise to the 8 known planets was concentrated in the inner solar system. By 30 to 50 astronomical units, the region of Neptune and the Kuiper belt, the disk was so diffuse that planet formation was extremely slow and inefficient. Building a planet of 5 to 10 Earth masses at 400 to 800 astronomical units from the Sun, within the few million-year window during which the protoplanetary disk was present before it was dispersed by the Sun's radiation and solar wind, is essentially impossible by any standard accretion mechanism. Outward scattering offers a partial solution. A protoplanet 9 could have formed in the giant planet region 5 to 30 astronomical units from the Sun, and been gravitationally scattered outward to its current orbital location by a close encounter with Jupiter or Saturn. This is the same mechanism that may have ejected a 5th gas giant in the NICE model. But scattering to 400 to 800 astronomical units while remaining gravitationally bound to the Sun is dynamically difficult. A planet scattered to those distances typically receives enough energy to escape the solar system entirely, becoming the kind of rogue planet we have been discussing. For it to remain bound, the scattering event must be finely tuned, delivering just enough energy to reach the outer solar system without exceeding escape velocity. And the resulting orbit should still be roughly aligned with the ecliptic plane, since the scattering event preserves much of the original orbital angular momentum. Planet 9's predicted orbital inclination of 15 to 25 degrees is harder to achieve through in situ scattering alone than through capture of an already inclined incoming rogue. The capture scenario, by contrast, makes the inclination entirely natural. A rogue planet approaching the solar system from an arbitrary direction would have an arbitrary orbital inclination upon capture, and values of 15 to 25 degrees are completely unremarkable. The capture hypothesis also receives support from a different kind of evidence: the demographics of rogue planets. The statistical analysis by Siraj and Loeb, using data from the microlensing surveys, established that free-floating planets in the mass range of Planet 9, a few to 10 Earth masses, are abundant in the galaxy. Critically, this mass range is the most common mass range for rogue planets, reflecting the fact that Earth to Neptune-sized planets are the most common type produced by planetary formation, and therefore the most common type ejected by planetary formation. A rogue planet in exactly the right mass range to match Planet 9's inferred mass, drifting through the Sun's birth cluster, is not a convenient fiction. It is a statistically supported expectation. Some might wonder whether the entire Planet 9 hypothesis is simply wrong, whether the orbital clustering is a statistical artifact that will disappear as more objects are found, and whether the anomalies it purports to explain have simpler explanations. This is a legitimate scientific position held by serious researchers. The Planet 9 hypothesis is not confirmed, it is a working hypothesis, well motivated by the data, consistent with multiple independent lines of evidence, but not yet proven by direct detection. The direct detection case is, however, advancing. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, renamed in 2020 in honor of the pioneering astronomer whose rotation curve measurements demonstrated the reality of dark matter, is currently under completion at Cerro Pachon in Chile. With an 8.4-meter primary mirror and a 3.2 gigapixel camera capable of imaging the entire accessible southern sky every 3 nights, the Rubin Observatory's Legacy Survey of Space and Time, or LSST, will detect thousands of new outer solar system objects within its first few years of operation, beginning in 2025. If Planet 9 exists, the Rubin Observatory is expected to either detect it directly or detect the additional extreme trans-Neptunian objects, whose orbital clustering will further constrain its parameters, or fail to detect it, which would be equally informative. The Rubin Observatory's survey represents the definitive near-term test of the Planet 9 hypothesis, and there is one additional piece of evidence, more speculative but deeply intriguing, that connects the captured rogue planet hypothesis to something even more profound. If Planet 9 is a captured world, it brings with it a compositional and geological history completely separate from the solar system's own formation. A world that formed around another star, or in the interstellar medium, would have formed from a molecular cloud with a different chemical composition than the molecular cloud that gave rise to the Sun and planets. The ratio of isotopes in its rocks, the abundances of trace elements in its interior, the specific mixture of volatile ices on its surface, all of these would carry the chemical fingerprint of a different stellar environment. For a world like Planet 9, cold, dark, located at 400 to 800 astronomical units, reaching it with a spacecraft is a generational challenge. At its predicted distance, a probe travelling at the same speed as New Horizons, which took 9.5 years to reach Pluto at 33 astronomical units, would take approximately 100 years to reach Planet 9's nearest predicted location. Technologies under development, laser-propelled light sails, nuclear electric propulsion, solar sails, could reduce this transit time substantially, but Planet 9 remains, for the foreseeable future, a world observed from afar rather than visited directly. What it would reveal, if we could reach it, is the answer to a question that has never before been answerable in the context of our own solar system. What does a world from another stellar system look like up close? But this raises an even bigger question, and it reaches far beyond the specific case of Planet 9. If stellar capture of rogue planets occurs, if it happened in our own solar system, then the boundaries between solar systems are not as absolute as we have always assumed. Planets are not permanently owned by the stars they orbit. They can be exchanged, they can be lost and gained. The solar system is not a closed system with a fixed membership. It is a dynamic entity that has been shaped by its interactions with the broader galactic environment over 4.6 billion years. This changes the conceptual framework for thinking about planetary origins in a fundamental way. Consider what it would mean for the question of life's distribution if planets can be captured. If a rogue planet can carry with it, preserved beneath kilometers of ice, a subsurface ocean that has been liquid for billions of years, then it carries, at least potentially, whatever life might have emerged in that ocean before it was ejected from its original system. The capture scenario does not merely import a world, it imports an isolated biological environment, frozen, dark, sealed. This is, at present, speculation. But it is speculation grounded in established physics. Subsurface oceans can persist on rogue planets through radiogenic heating. Life, if it emerged, would be confined to that subsurface liquid environment, isolated from the surface. Capture by a new star system would not dramatically change the conditions in a deep subsurface ocean. The ocean is insulated from surface conditions by kilometers of ice, and the primary heat source is internal, not stellar. The concept of a rogue planet as a potential vehicle for the interstellar transport of life connects to one of the most audacious ideas in astrobiology, lithopanspermia, the hypothesis that life can be transferred between planetary systems embedded in rocky material or icy bodies. Traditional lithopanspermia imagines microorganisms surviving inside fragments of rock ejected by asteroid impacts, drifting through space and eventually landing on another world. The distances involved in interstellar transfer make this process improbable for individual rock fragments. But a rogue planet is a far more robust vehicle than a rock fragment. It carries a massive, thermally insulated liquid water environment, the conditions for biological preservation over timescales of billions of years, not the exposed rock surface and vacuum that would kill most organisms within years. If life exists in rogue planets' subsurface oceans, the capture scenario represents a mechanism for interstellar biological transfer that operates on scales and timescales relevant to galactic biology. This is speculative, emphatically so. But it is scientifically structured speculation, a hypothesis that follows from established physics and that makes specific, testable predictions, and it illustrates the depth of implications that follow from confirming a single captured world in our own solar system. Let us step back from astrobiology and consider the implications of capture for our understanding of solar system formation more broadly. The NEAS model, the most influential framework for understanding the dynamical history of the early solar system, describes a period approximately 700 million years after the formation of the planets during which the gas giants underwent significant orbital migration. Jupiter moved slightly inward. Saturn, Uranus and Neptune moved outward. The orbital resonances between the giant planets destabilized, driving a period of intense bombardment of the inner solar system, the late heavy bombardment, evidence for which is recorded in the cratering records of the Moon, and ejecting enormous numbers of small bodies from the outer solar system into the Kuiper belt, the scattered disk and the Oort cloud. This period of dynamical upheaval is also the period during which planetary capture would have been most likely if the Sun was still in or near its birth cluster. The chaotic gravitational dynamics of the giant planet instability would have created frequent three-body encounter conditions in the outer solar system, exactly the configurations needed for a passing rogue planet to be captured into a stable orbit. A rogue planet drifting through the solar system during this period of upheaval could have had its trajectory altered by simultaneous gravitational interactions with Jupiter and Saturn in a way that left it in the distant inclined orbit now attributed to Planet 9. Subsequent dynamical evolution over 4 billion years of solar system history would have shifted the orbital parameters somewhat from the capture configuration. The long-term gravitational influence of the four known giant planets slowly modifies any distant orbit over billions of years, but the basic signature of a captured object's orbit persists far longer than the age of the solar system. What does this mean for the search for Planet 9? Current observational constraints allow a wide range of possible locations for Planet 9 along its predicted orbital track. The orbit covers such a vast area of sky, thousands of square degrees, that even a dedicated search has not yet managed to survey the full parameter space at the sensitivity required to detect an object of Planet 9's predicted brightness. At 400 astronomical units, a Neptune-sized world reflects so little sunlight, approximately 10,000 times fainter than Neptune, that it is invisible to current survey telescopes except under ideal conditions. The Rubin Observatory's LSST represents the most powerful upcoming tool for this search, but even Rubin's sensitivity does not guarantee detection. If Planet 9 sits at the far end of its predicted orbital distance, 700 or 800 astronomical units, it may be beyond Rubin's detection threshold. In that case, detection would require next-generation infrared telescopes capable of detecting the thermal emission of a cold, distant world, the residual heat from Planet 9's own internal radioactivity glowing faintly in the far infrared. The Nancy Grace Roman Space Telescope, with its wide infrared field of view and proposed future missions to the far outer solar system, represent the longer-term detection path. A dedicated outer solar system survey mission, specifically designed to characterize the trans-Neptunian population and search for Planet 9 class objects, has been proposed in various forms in NASA's planetary science decadal surveys. Meanwhile, the search continues with existing facilities. The Subaru telescope on Mauna Kea in Hawaii, with its Hyper-Suprime Cam wide-field imaging system, has conducted dedicated outer solar system surveys at sensitivity levels approaching what would be needed to detect Planet 9. Japanese astrophysicist Patrick Sophia Likauka and colleagues have proposed alternative distant planet hypotheses based on Subaru data, arguing for a somewhat different mass and orbital configuration than Brown and Batygin predict. A reminder that even within the Planet 9 framework, the specific parameters remain actively debated. What is not debated is the observational reality of the anomalies that demand explanation. The extreme trans-Neptunian objects are real. Their orbital clustering, across the highest quality datasets with the most careful bias analysis, remains statistically significant. The highly inclined outer solar system population is real. The sun's anomalous tilt relative to the ecliptic is real. Something is causing these things. Whether that something is Planet 9, as Brown and Batygin predict, a somewhat different, massive distant object, or an as yet unconceived alternative mechanism, that question remains open. But the capture hypothesis adds a dimension to this search that goes beyond the astronomical. It transforms Planet 9 from a missing piece of the solar system puzzle into a potential emissary from another stellar system. A world with a history, a provenance, an origin story that predates our Sun. Let us sit with the profound strangeness of that possibility for a moment. Every rock on Earth, every element in the periodic table that makes up your body, every photon of sunlight that has ever warmed this planet, all of it traces back to the molecular cloud from which our Sun formed 4.6 billion years ago. The solar system is, in this sense, a closed chemical system. A family. Everything in it is related. But if Planet 9 is real, and if it formed around another star, then somewhere in the outer solar system there is a world made of different stuff. Atoms forged in a different stellar interior. Rocks whose radioactive isotope ratios carry the timestamp of a different star's history. Ices whose molecular compositions reflect the chemistry of a different protoplanetary disk. A geological record that began before the Earth existed and in a completely different place in the galaxy. That world is not exotic. It is not small. It is, if the mass estimates are correct, a super-Earth or sub-Neptune, larger than our own planet, with more mass, more internal heat, and more geological complexity than Earth. And it is, if it exists, in our solar system. Our Sun's gravity holds it. Its elliptical orbit brings it no closer than roughly 200 astronomical units at perihelion, farther than any currently visited body in the solar system. But it is here, in the same gravitational family as Earth, captured billions of years ago and orbiting ever since. This is not science fiction. It is a scientific hypothesis, grounded in real data, consistent with established physics, and testable within the next decade. We began with a number. 8 planets, clean, settled, memorized by every school child. A number that has defined the solar system's identity since the reclassification of Pluto in 2006. And we have followed the evidence through the orbital clustering of extreme trans-Neptunian objects, through the dynamics of the Sun's birth cluster and the physics of three-body capture, through the demographic reality of a galaxy populated by hundreds of billions of rogue planets, through the specific and converging lines of evidence pointing towards something massive hidden in the outermost dark, to a place where that number looks provisional, uncertain, possibly wrong, not because the 8 known planets are not real, but because there may be a ninth one, and its history, if the capture hypothesis is correct, would be unlike any other world we have ever studied. Born around another star, or born in the interstellar void itself, cast out into galactic darkness, drifting through the gap between stellar systems for some unmeasured span of billions of years, until the sun's gravity reached out and claimed it. A planet that belongs to our solar system now. That has always been invisible to us, not because it is not there, but because we have only recently developed the tools to recognize its gravitational fingerprints. The Vera C. Rubin Observatory, as it begins its decade-long legacy survey of space and time in the coming years, will either find the additional extreme trans-Neptunian objects that confirm Planet 9's existence, reveal Planet 9 directly in its imaging data, or constrain the hypothesis to the point where the scientific community must seek alternatives. Within this decade, we will know substantially more than we do now. One thread remains open, and it is the deepest one. If Planet 9 is real, and if it is a captured rogue world, we do not know where it came from, what star it originally orbited, or whether it ever orbited a star at all, how long it drifted before our sun claimed it, whether its subsurface, if it has one, is frozen solid or liquid and dark and ancient, whether anything, any chemistry, any biology, any remnant of processes that occurred in a completely different stellar environment came with it. These questions cannot be answered by the Rubin Observatory. They require a mission, a spacecraft aimed at the outermost dark, travelling for decades, arriving at a cold world that has never been visited and may never have been seen. That mission does not yet exist. But the question demanding it does. As we continue to survey the outer solar system, as each new trans-Neptunian object adds a data point, as the theoretical models grow more refined, as our instruments grow more sensitive, the edge of the known solar system keeps moving outward. What it finds there may rewrite the solar system's entire history.